This is an introduction to distributed quantum computing that was originally designed for an audience of PhD students that worked in quantum computing, specifically from the physics or chemistry background, so more of the applications oriented side of things, or were working on the theory of these applications but had never necessarily been in contact with the system architecture side in computer science. Related to quantum computing, and well, specifically, this is an introduction to that systems thinking in the sphere in which I'm working, which is distributed quantum computing. So let's get right into it. First of all, what is distributed quantum computing? Where for me, distributed quantum computing means having multiple quantum computers that are connected with each other, and they are connected with each other in order to jointly perform a computation that is larger than themselves. So no quantum computer could individually perform this computation, so they have to collaborate with other quantum computers and communicate through some network in order to achieve this goal. This is basically how most of reasonable HPC compute occurs in the classical world at the moment. And I have an asterisk in the word interconnected because you can interconnect quantum computers via both classical communication and quantum communication. Doing so via classical communication is incredibly expensive at scale. So when I talk about distributed quantum computing, I usually mean quantum computers interconnected via quantum networks, which usually also implies classical networks. It means basically a hybrid network where you've got both, rather than classical networks simply because it's not a solution that scales. And the whole point of distributed quantum computing is scaling quantum computing. Now, how do we do this at the moment? Well, we take a very large computation that wouldn't fit into one device, we abstract it to some sort of intermediate abstraction, and then we cut up that abstraction in a way in which every QPU in our network could be assigned a different subsection of our original large computation. That looks a little bit like this. Well, first you have multiple types of large computations that may arise depending on the model that you're working with. The most popular model is the circuit model. So in circuits, what we usually do is we build a hypergraph in which vertices, so these nodes, are qubits and edges are gates. You know that there are 1-qubit gates in a circuit, so that would look like a hyperedge like this, where it's self-contained. Then you might have 2-qubit gates, hyperedges that contain 2 nodes, and 3-qubit gates, so default gates, for instance, which contain 3 qubits, so 3 nodes. These hyperedges are usually cut up by a solver of BHP, balanced hypergraph partitioning. I'm going to go into all these steps a little bit more in detail. So first of all, what is balanced hypergraph partitioning? Well, that comes with the definition of what is its input, the hypergraph, this abstraction. A hypergraph is very similar to a graph. The difference is that instead of having two-way relationships, so relationships where 2 vertices, 2 nodes are connected, it has multiple nodes that can be grouped into one single relationship, so one single hyperedge. You can think of it as groupings rather than, two-way lines. The hypergraph partitioning problem aims to have a hypergraph cut up into n different partitions in which when we're cutting up, we aim to minimize the number of hyperedges that cross the partition boundaries. So every single time we have a hyperedge that lives in multiple partitions, that comes at a cost. The balanced version of the hypergraph partitioning problem also aims to have these partitions be roughly equally sized. So each partition has about the same number of nodes. Most of the current literature utilizes bound hypergraph partitioners that have this roughly equally sized demand as their baselines, or they do the testing of their partitioners in this setting too. This would be equivalent to a setting where you have a heterogeneous network in which every single device is basically the same type of device or has about the same type of qubits available. It's not realistically the long-term view, especially if we're looking at building things like the quantum internet, but it is a step in the direction of that first stage of building the first distributed quantum devices. Now, I said that we have different hyperedges that live between partitions. As we've said before, a hyperedge is equivalent to a gate. So what does it mean to have a cross-partition gate? Well, it means to have a non-local gate, so a gate that is living between 2 devices, Alice and Bob. Alice and Bob are, as I've said before, in the setting that I usually work in, connected via classical channel or quantum channel. And the way in which they're going to perform a non-local gate, so in this image you see examples of CNOTs being implemented, non-local CNOTs being implemented. They're going to both have some device qubits that they will utilize as, let's say, the original target and control qubits, and then they will have some sort of communication qubits that will be entangled. This entanglement will be an EPR pair that has been priorly distributed by the network that they're going to consume in order to perform the non-local gate, which will be performed via a classical forwarding of measurements from Alice to Bob, as well as this entanglement, so this quantum resource being consumed by both parties in order to perform the non-local gate. These non-local gates can be implemented in through different primitives. So I've described the teleportation primitive, but there's also CAD communication that is also available depending on the device that you've got and the inherent structure, the inherent architecture of it. You might be restricted to one of these two ways of communicating, or one of them might be better in terms of the noise that it leads to within your device. Now, to solve the Phalen's hypergraph partitioning problem, we have multiple solvers that we have inherited from other areas in science, such as graph theory, a very well-known solver that is not the most advanced, but it is relatively well-known and is very often used as the initial state for more complicated solvers, more complex solvers, is the Fuda-Mathias partitioner. The way it works is it takes a hypergraph. So in this setting, you see a hypergraph kind of designed as a graph in which, these edges that interconnect nodes that have certain symbolism to it might represent more than two-way relationships. So for example, you have C, E, and F being connected by the same type of lines. And that's kind of how they represent the hyperedges in this kind of non-grouping abstraction. But you have your hypergraph and you have two partitions. And basically, the name of the game is to evaluate what would be the cost of moving every single one of these nodes to the other partition. So for example, if you moved node D to this partition, this hyperedge that is connected to C and D would no longer be non-local. It would no longer live between partitions because C and D would be in the same partition. But now this hyperedge that lives between D and F would be non-local because D would be here, F would be here, and there would be a crossing. So that would be a zero net cost because you would have lost one and you would have gained one. You do this calculation for every single node and you basically order them and you check which node was the one that led you to a highest gain, essentially, and you log that one in. You do this iteratively until you have logged every single node in. It is a heuristic because this problem is NP-hard, and obviously it has all the fallacies that a heuristic may have, such as falling into local minima, but it's one of the partitions that can give you an insight into the flavor of how this problem is being solved. Now, the balanced hypergraph partitioning problem, even though it's NP-hard, is still a simplification of the story. In reality, our only input to our problem, to the distributed quantum computing mapping problem, essentially, is not only a large computation, but the actual graph that represents the network that we're working with. So this graph, this network that we have, will have devices that have different capacities. Will have different bins that need to be filled. You cannot assign more qubits than a device can do at a certain time point to any device. So you need to respect capacities, which the hypergraph partitioning problem, even in its balanced setting, doesn't do, at least through its normal definition. Then you might have different devices connected via different channels. You may have some devices that have quantum channels, but others that do not. So, learning how to respect those real architectural constraints is an input to the problem. So it's slightly more complicated. Now, most of the literature and most of the work that exists in an advanced form at the moment is seeing it through the simplified lens. This will hopefully evolve with time. The field is already going towards evolving through this, but this is kind of the state of the art right now. Now, solving the distributed quantum computing problem, this mapping problem that I've described, is not the same as doing qubit routing in one device. This is a very common misconception that I've seen amongst people. This is why this slide is so overwhelming. But just so you get the idea, the actual devices are completely disconnected. It's not the same as saying I'm going to move, a series of operations from one side of my device to another. This is generally talking about, I have different machines that have different software layers that now need to collaborate with each other. I'm going to consume EBITs, bell pairs, EPR pairs between these devices and classical bits to perform this communication. I actually have to consume this entanglement, which is a resource that comes from somewhere else. It comes from a provider, from a network that's giving it to me. I might be able to play certain games which might enable me to reduce the amount of noise that I have in these non-local operations. So for instance, you can have a setting where you consume multiple EPR pairs of bad quality to create a better quality EPR pair. Like you have to schedule these operations and the entanglement. It is generally a much more complex setting than just classical. The routing that we're used to seeing in certain types of quantum devices, such as supercomputing devices, superconducting, sorry. Now, what is the current state of the art in distributed quantum computing? Well, we're having um, campus and city level quantum networks that already exist that connect multiple devices. We have companies claiming that this will be a multi-million-dollar business. We have large global corporations such as Cisco that enable the current classical distributed computing world, saying that the future of quantum computing is distributed, which I highly agree with. And then we have collaborations between the big giants, let's call them, such as Cisco and IBM, to get to a stage where we're doing distributed quantum computing. There's a lot of movement, there's a lot of promise from both industry and academia, and a lot of people have distributed quantum computing in their roadmaps in one form or another. But the reality is nobody at this stage has publicly announced having a reasonable compute interconnected via quantum networks. What do I mean by a reasonable compute? I mean more than 40 qubits on each side. Like actually being able to perform distributed quantum computation that wouldn't be simulable in either side of that distributed setting, even if it's a two-way distributed setting with only two devices. So I think this is the first step towards the future of the field in terms of implementations. And the second step are the very famous and very promising quantum data centers where you might have multiple devices interconnected within the same room via a quantum network and collaborating with each other. This is the more, marketing friendly next step that a lot of companies are talking about. In this setting, you'll basically have a software layer in which you're doing your applications and your optimizations, and below it will live a network layer that you as a user might not necessarily have access to or want to play with unless you are specifically working in optimizing, distributed quantum computing. This is already kind of the case when you access HPC. You can have the ability in certain data centers to, access the communication MPI layer, but for most users, you're just accessing the top level layer. You don't see the distribution, but believe me, it does exist, below you. Now, a more long-term view after quantum data centers are what I consider to be, the final goal of quantum computing, which is hybrid data centers. So data centers where you have both classical and quantum compute collaborating with each other, when you have some level of offloading of computations to quantum devices, because we know they're optimized for that. This is already the mindset that some people in industry and academia are approaching quantum computing from. There are hybrid data centers per se, but they, again, don't necessarily have reasonable compute, and they definitely don't have offloading in the sense of I'm going to send some primitives to my quantum device and I have specific software to recognize these primitives and just forward them. It's much more manual, it's much more, experimental. After that, there is the quantum internet. So the quantum internet is this promise, is this vision that there will be essentially a network provider that will enable different government bodies, universities, companies to connect themselves to a global quantum network in order to, for instance, pool resources between two universities who are in different parts of the world, who might not have a ownership over a quantum network and who might want to pool their resources in order to do some sort of research. They both have, 1,000 qubit quantum computers and they want to do some research together that requires 2,000 qubits. So there will be a network provider that will be accessible by these quantum devices in which they will be able to pull these resources together. This is a much more long-term view. It also comes with different implications and different discourse depending on what we're talking about. I mean, there's a lot of discourse in the world about the quantum internet in the setting of security. And there we're talking about genuinely having a quantum layer on top of the classical layer for most internet communications that assures a level of security that classical communications cannot do. I'm not a security expert, but just from the laws, the fundamental laws of quantum information and classical information, there are certain leakage assurance. So you can leak information in the way you communicate. You can give an enemy or somebody who's trying to learn something about your system, some information just by the way that you move without necessarily giving them access to the data. So this leakage can be in some settings avoided or minimized by quantum information, not by classical information, which inherently makes it more secure, at least from a mathematical perspective. So a lot of people talk about the quantum internet in the setting of like, oh no, we're really gonna have like everything be quantum. Uh, because I work in distributed quantum computing, I see it more as there will be some sort of service that is accessible by these quantum devices in order to complete long range computations together collaboratively. Now, I am not crazy. Distributed computing is completely real. Here's a little bit of a quick timeline of how distributed computing is generally in its very core computing. I mean, everything is distributed. Um, we are currently in the quantum sphere, moving away or moving into the 60s, maybe very early 70s. I mean, we are at the start of this timeline, and this timeline in the classical world already pointed to distributed computing, and quantum computing has the exact same reasons to go down the distributed route, but on top of the reasons that the classical community had, it also has the reality or the real setting in which quantum computers are so noisy, and it's so difficult to actually get these qubits to be protected without them leaking into each other, without them affecting each other. And talking about devices that will have millions of qubits within one single chip is very unrealistic. Um, so, as an aside from that rant, there are genuinely quite a lot of advantages for using quantum computing in distributed settings to solve distributed problems. You know, I, obviously everybody loves chemistry and everybody loves talking about how the first application of quantum computers will be chemistry, but there are so many CS problems where there is such a real incentive to use quantum computing because it offers very real advantages in terms of the resources that are utilized. And these are problems that are essential to the running of our everyday activities. I mean, there is really a lot of work in proving and showing that distributed classical CS problems present a quantum advantage. So this is really an important area of quantum advantage that, in my opinion, is not as popular or as explored as it should be. So there are, reasons to believe in distributed quantum settings beyond just the fact that it will be a necessity from an architectural standpoint. But there is real advantage in doing distributed quantum computing. Now, as I've said before, we have our old and well-known enemy, noise. In distributed quantum computing, we're not only dealing with QPU noise, which is pretty problematic, but we're also dealing with network level noise. So we have injections of noise coming from the network that are affecting and decaying our computation. Here is a figure from ongoing work that we're doing in collaboration with the error correction team in the University of Edinburgh and the University of Heriot-Watt, which is also in Edinburgh, where we are basically looking at how this noise affects computation. This is a simulation of simulation. This is an implementation of circuits that are supposed to create JZ states on the current IBM Kingston device. It is a real implementation. The way in which we perform non-local gates is by having our local, so what would be within one QPU computations on different parts of the device, and we're basically implementing the circuit that would implement non-local gates in a local form. So we're basically somehow emulating or simulating distributed devices within a real quantum device. And as you can see, for a monolithic, so this would be for just straight up, I'm running the normal circuit on my device. I have a very rapid decaying quality from what I'm expecting my fidelity to be to where it is as I grow in the number of qubits that I'm utilizing. But that's even worse. I mean, we start with less than half of the quality that we should have when we are testing it with distributed routines. And obviously the decaying comes faster and is even worse. So, this noise is a real problem. Um, And beyond the noise and beyond the promise or the reality that there needs to be a lot of research in error correction and in error noise mitigation for distributed settings, another area that I've kind of been exploring recently is asking the questions of in the normal, quantum computing pipeline, we have a lot of things that we need to do, such as circuit optimization and, as I've said, error correction, error mitigation. Where should we do them? Should we do them on the original circuits, or should we do them on the circuits after they are partitioned? I call this global and local encodings, and a couple of my recent papers were on that. But essentially, what I aim to say with what I aim to explain with this presentation in some level has been kind of giving you an overview of what the field looks like, what research or open questions in this field might look like, to hopefully make you excited and interested in distributed quantum computing. Thank you for listening.